Thank you, Jim, and hello, everyone. I'm happy to be here on the ITT event and very excited to speak about Panther Lake architecture, which is our next generation mobile processor. Panther Lake primary target was taking Lunar Lake previous generation efficient architecture and scale it to higher volumes while delivering higher performance using Intel 18A process. We have increased the architecture flexibility to support multiple compute configurations, as well as memory and IOs across the segments. In order to support the broader mobile market, we have also enhanced the platform to allow flexible OEM integration with regards to power delivery and memory on board. This allowed us to scale performance across core, graphics, and AI workloads while maintaining efficiency and further improving it. Let's learn about the architectural flexibility. Panther Lake builds on the architectural strength of both Lunar Lake and Arrow Lake previous processors. We inherit Lunar Lake x86 power efficiency and leverage performance scaling from Arrow Lake. We inherit with both. Panther Lake delivers a powerful mobile processor across a wider range of segments. Panther Lake utilizes our fabric together with a mature Foveros packaging to separate the GPU from the compute tile, allowing graphics to scale across segments and also to group all IOs under one tile. The primary element of the architecture for scalability is the Scalable Fabric Gen 2, which originally was developed in Lunar Lake. There are three key elements that makes this fabric so special. First, it can be used over multiple physical layers. Specifically in Panther Lake, it is used for Foveros advanced packaging. Second, it uses one transactional protocol layer, which can be used within the tile or across tiles. This is what makes it partition agnostic. And third, it can carry multiple functional protocols, what makes it IP agnostic. These fundamental elements allows us to support a wide range of IPs and tile combinations. One of the key changes for scalability in Panther Lake is the separation of the GPU from the compute tile. Thanks to the flexibility of the fabric, this separation was straightforward to implement. We use a die-to-die interconnect between the GPU tile and the compute tile, allowing them to communicate efficiently as if they were part of one unified system. This modular approach gives us more design flexibility, and you will see later how it helps scaling graphics performance. Now let's look at Panther Lake's modular tile-based construction. At the center, we have the compute tile, with most of the computing elements and the memory subsystem. Next to it is the GPU tile with the graphics engine, which has been separated from the compute tile. We use the separation to scale the graphics tile independently from the other tiles, delivering the required graphics amount of performance per segment. On the top right corner, you can see the platform controller tile, as in Lunar Lake, with connectivity, security, and platform-level functions. These three tiles are assembled into one package using Intel Foveros technology on a passive die, creating compact, yet a powerful chip. Panther Lake supports both LP5 and DDR5 technologies, with 128-bit LP5 up to 9.6 giga transfer per second and up to 96 gigabyte capacity, and with 128-bit DDR5 up to 7.2 giga transfer per second and up to 128 gigabyte capacity. Both enable robust throughput and responsiveness across compute and graphics workload. To allow platform board flexibility and supporting broader set of segments, while Lunar Lake invested in a dedicated PMIC for power delivery and also integrated memory on package, Panther Lake will allow platform design optionality. For power delivery, Panther Lake will unleash the use of higher currents with discrete VR topology to meet engines' horsepower and a wider range of platforms. And for memory, with both LP5 and DDR5 support, OEMs can have the flexibility of selecting the right technology, speed, and capacity that fits the platform. As Jim showed, Panther Lake supports 3 configurations. The first is a basic configuration that delivers great balanced mobile performance. The second is a more performing configuration for demanding general-purpose compute. And the third, in addition to the more performing general compute, delivers superior graphics and content creation performance. While each of the 3 can operate in a wide range of platform thermal envelopes, we have designed them with a single package. This allows OEM to find the right configuration to the right form factor, and it also allows more than one configuration for a specific form factor. Let's have a deeper dive into each of them. This slide shows Panther Lake first basic configuration, highlighting the key component across the 3 tiles. Starting with the compute tile on your left, it has a powerful mix of 4 performance cores sharing a last level cache, forming a performance cluster, and 4 efficient cores forming an efficiency cluster. The 2 clusters together are designed to handle a wide range of workloads. The compute tile also includes our imaging processing unit, or IPU 7.5, for advanced imaging acceleration, the neural processing unit, or NPU 5, for AI task acceleration, and the Xe and display engines. Memory-wise, it supports LP5 up to 6.8 giga transfer per second, and DDR5 up to 6.4 giga transfer per second. We can also carry over the successful 8 megabyte memory cache to boost performance and efficiency. Next, the platform controller tile. On your right, includes 12 PCIe lanes, 4 Thunderbolt ports, 10 USB ports, and wireless support with Wi-Fi 7 and Bluetooth 6. On your bottom right, we have the GPU tile that is built on the new Xe4 architecture, featuring 4 Xe cores and 4 ray tracing units. This setup provides efficient graphics capabilities for mainstream workload. Looking at the tiles together, they form a powerful, well-balanced configuration. Now let's look at the second, more performing configuration, which brings upgrade to the compute and the platform controller tile. The compute tile upgrades the performance cluster to 4 P-core and 8 E-core config. And together with the efficiency cluster, it supports a powerful 16-core configuration. As you can see, the memory bandwidth is boosted. In this config, we support LP5 up to 8.5 gigatransfer per second, and DDR5 up to 7.2 gigatransfer per second. The platform controller tile now supports 20 PCIe lanes, up for 12 in the basic configuration, with additional 8 Gen 5 PCIe lanes, enhancing connectivity for higher performance devices. These upgrades make this config ideal for more core-centric, demanding workloads, while keeping the same GPU, NPU, and IPU setup as in the basic configuration. Now, switching to the Panther Lake third configuration. The compute tile retains the 16-core config, along with the same NPU, IPU, media, and display engines. Memory bandwidth is further optimized. LP5 is now reaching up to 9.6 gigatransfer per second, or bandwidth of around 150 gigabytes per second, and offers the highest throughput for memory-intensive tasks. As you can see, the platform controller tile remains consistent with the basic configuration. But the biggest upgrade is the GPU tile, which moves from the lighter version to a wide config. It features 12 Xe cores and 12 ray tracing units, tripling the graphics compute compared to the previous configuration. This makes it ideal for graphics-intensive workload like gaming, content creation, and AI inference. Overall, the third configuration delivers top-tier compute and graphics performance while maintaining package footprint consistency. So after we went through each of the configurations, let's recap on Panther Lake's lineup, comparing the 3 configurations side by side. Starting with the CPU, the configuration scales from 8-core in the basic config to 16-core in the 2 more performing configs, both with the same core mix of 4 P-cores and 8 E-cores in the performance cluster. For the GPU, while the first 2 configurations include 4 Xe cores, the third config jumps to 12 Xe cores, tripling the graphics capability to deliver discrete class performance. Memory bandwidth improves as you scale from 6.4 gigatransfer per second to 9.6 for LP5, and from 6.4 gigatransfer per second to 7.2 for DDR5. And as we have seen, I/O capacity also scales from 12 to 20 PCIe lanes. Across all 3, the NPU, the IPU, the media, and display engines share the same configuration. All configuration also supports a wide set of connectivity with Wi-Fi 7, Bluetooth 6, and Thunderbolt, ensuring consistent connectivity across the stack. So now that we have seen how Panther Lake scales across the segment, let's see how we scale performance across all major IPs. Starting with the cores, Panther Lake upgrades our 2 cores. Cougar Cove is the code name for the performance core, or P-core, and Darkmont is the code name for the efficient core, or E-core, which is used for efficient multi-thread scaling or for casual usage. Both cores were designed and optimized for 18A. They deliver better performance at lower power and optimized IPC. On the next session by Steven, you will get deeper dive on the core's architecture. Now let's have a look how the cores are clustered together with the caching hierarchies used in Panther Lake. Highlighted on the top is the performance cluster, which uses both P-core and E-cores, as I've shown in the previous slides. Panther Lake supports two config, a 4-core config, which means 4 P-cores without E-cores, and 4+8 config, which means 4 P-cores and 8 E-cores. The performance cluster cores are connected through a scalable high-bandwidth fabric and shares a last-level cache to optimize bandwidth and latency. Below the performance cluster, the efficiency cluster is highlighted. It is based on a 4 E-core module with L2 cache. It has a dedicated power delivery with dedicated power management and is connected directly to the memory subsystem. To maintain data consistency across these clusters, coherency is managed through a system-level home agent, along with cache coherency agent embedded in the clusters. This ensures seamless communication and synchronization between the cores, regardless of their cache hierarchy. Now that we have covered the core cluster, let's turn to the GPU. Panther Lake introduces the new Xe3 graphics architecture, designed to scale up performance without compromising on power efficiency, which is critical balance for modern workloads on mobile. This architecture supports up to 12 Xe cores and up to 16 megabytes of L2 cache. It also supports up to 12 ray tracing units and up to 120 peak tops. And speaking of AI, Panther Lake enhances further its AI acceleration capabilities with the new NPU 5. The next-gen NPU delivers high performance in small footprint, optimized for both area and power efficiency. Compared to the previous generation, Gen 5 offers 40% improvement in performance per area versus Lunar Lake, and 3.8x more tops over Arrow Lake H, supporting up to 50 peak tops. NPU 5 also adds support for floating point 8 for better efficiency in relevant AI models. This marks a major leap in Intel's AI strategy, bringing high-performance, low-power inference to the front of Panther Lake's architecture. The imaging processing unit went through significant upgrades as well. Panther Lake integrates IPU 7.5 that is designed to deliver clear and realistic stills and video. The engine features AI-based noise reduction and local tone mapping for clean and clear image with better contrast and brightness. It supports hardware-accelerated staggered HDR to enable dynamic range capture. And very important, it delivers up to 1.5 watt power reduction compared to the previous generation using hardware staggered HDR. This is critical for battery-sensitive devices. Our Xe media engines comes with a broad set of codec support. Panther Lake added capability for AV1 444 decode and encode for enhanced screen sharing. It also added AVC 10-bit decode support used for prosumer cameras, which extends the Sony XAVC family. These changes are added to support the wide variety of formats which our media engines support. Moving on to the architecture efficiency. Lunar Lake already established that x86 has leadership power efficiency, and Panther Lake will follow. Let's focus on the SoC efficiency features. We started with a low-power island in Arrow Lake with 2 cores and 2 megabytes of cache. In Lunar Lake, we introduced a new efficiency cluster, and Panther Lake is leveraging it with an upgrade to the Darkmont E-core. This is a major upgrade over the Arrow Lake low-power island. It is more performant and therefore can support a wider range of tasks, from backend services to medium compute workloads, while maintaining low power draw. This enhanced cluster is a key feature for Panther Lake's efficiency. Panther Lake also leverages the memory side cache architecture introduced in Lunar Lake. The main value of this 8 megabyte physical cache is squeezing more performance out of the efficiency cluster. It improves latency and bandwidth, which increases the core IPC and reduces DRAM traffic with reduced power consumption, which buys us headroom for core frequency. It also enables efficient caching for devices such as media or NPU, which is especially valuable in low-power scenarios. This enhancement complements Panther Lake's efficiency cluster, allowing more workloads to run in a lower power overall. Now let's look at the dynamic runtime behavior with Intel Thread Director scheduling and the active power management enhancement. We had 3 goals: efficient dynamic frequency scaling, widening the coverage of our models for more usages, like platform types, operation systems, and KPIs, and providing more consistent behavior across software modes. For achieving that, we optimized the overall scheduling model by enhancing the load classification training models and used a more realistic user training environment. The 2 allowed us to further move P&P decisions from software to SoC for tight control, as well as deliver AC versus DC experience consistency. We also delivered simultaneous thread execution feedback across the different cores and improved the telemetry we advertised to the SoC. With that, we deliver more consistent behavior across software mode of operations. And in addition, we deliver more consistent experience across different operation systems, like Windows, Chrome, and Linux. We believe that the changes will be consumer visible and will improve user experience. We have designed Panther Lake with aggressive goals across all domains. I'll start with the CPU. Our focus was increasing performance while improving efficiency, which means not only increasing peak performance, but also delivering the same amount of performance in lower power. We deliver more than 10% single-thread performance at similar power versus Lunar Lake. We have increased multi-thread performance at similar power by more than 50% versus Lunar Lake. And we deliver Arrow Lake similar performance at over 30% less power. Moving to the GPU, we aimed for significant performance scaling, and indeed, we have scaled the engine performance by more than 50% versus Lunar Lake and versus Arrow Lake. This will significantly enhance graphic experience. For the NPU, we have focused on improving area efficiency, which means packing more AI capabilities into a smaller footprint. which is critical for mobile deployments. The result is 40% more TOPS per area versus Lunar Lake. For the IPU, we focused on AI-based features as well as hardware staggered AGR, which improved power by up to 1.5 watt versus software staggered AGR. And finally, on the SoC power front, we targeted Lunar Lake power levels, and we have exceeded the target. Panther Lake improves SoC power by up to 10% versus Lunar Lake, and more than 40% versus Arrow Lake. As you've seen, Panther Lake brings a wide range of mobile segments with an upgrade to all the IPs, the memory, the connectivity, and also the IOs. And as Jim showed at the beginning, Panther Lake offers performance with enduring efficiency. It leads in AI. It leads in mobile gaming. It's loaded with connectivity and IOs. And it is built with Intel's 18A latest process technology. I personally can't wait to see Panther Lake systems early next year and get your feedback on it. And with that, I would like to invite Steven on stage, and thank you all for listening.